Okay, today we're going to talk about integration by parts, but first I just want to mention that this is one of the drawbacks for flipping the class is that there really is not a time when you have a night off after a test, and I didn't want to give you homework this weekend, so you're going to watch this video in class. Hopefully that'll be okay. We will have gone over the test and talked about a few things before you do that. So in essence, you might not have homework tonight, so that's good. Okay, so integration by parts. What is it and where does it come from? If U and V are different functions of x, or differentiable functions of x, and two different types of differentiable functions of x, then by the product rule, if I take the derivative, it's the derivative of the first with respect to x. So that'd be du over dx times v plus the derivative of v times u. So u times dv dx. Okay? If I integrate both sides of this equation with respect to x, well, then I would just get uv on the left. And on the right, because I'm differentiating with, because I'm integrating with respect to x, the dx's are going to cancel. So I will have the integral of v du plus the integral of u dv. In essence, those cancel. So, integration by parts when you have two different functions, and we are used to defining in terms of u. So if I solve for the integral of u dv, I get uv minus the integral of v du. And that's where integration by parts comes from. You have choices of what you choose for u and v. Some choices are better than others. Some work out better than others. There is a guideline to help you choose your u, and by choosing your u in this order, you make the problem easier. Not saying that it's the only way you can do it, but it does make it easier to do it this way. And the mnemonic device we use is liate, or however you want to say this word. I think liate, but and if you have a logarithmic function, u is the logarithmic function. If you don't have logarithmic, then you go to inverse functions, and that's what your u is. If you don't have inverse functions, then u is your algebraic function. If you don't have algebraic, then you move to trigonometric, and your last choice is exponential. Here are some examples. So when I look at this function, x, integral of x cosine x, I can't use a u substitution because I can't get the x in the problem other than the cosine x. And I know that the derivative of cosine x, or the integral of cosine x, is going to have a trig function in it, so that doesn't help me either. So, let's see, I have an algebraic and a trigonometric function. So which one comes first? Algebraic comes first. So that is my u. So my u is x. That means my dv is what's left over, cosine x. So I go over here and fill in what I don't know. So if dv is cosine x, whose derivative is cosine? It's sine. And du would be dx. So this integral x cosine x would equal uv x sine x minus the integral of v du, sine x dx. So I have one more integration to do. So I have x sine x, whose derivative is sine negative cosine. Put that negative here. With that, we'll make that positive cosine x. And don't forget your cupcake. It's really quite easy as long as you remember liate and what order to choose u in. It can become much more difficult if you don't pick the right u in the right order. Okay? So, second one, we have x e to the x. So I have algebraic and exponential. Algebraic is first. So u is x, dv is u to the x. So that means if I integrate e to the x, I get e to the x. I don't worry about the plus c because I know I have to put that in my integral when I'm doing the actual integration of the problem. du is dx. So this integral becomes uv x e to the x minus the integral of v du, e to the x dx. So when I integrate e to the x, I get e to the x. Don't forget your cupcake. So you can see that this becomes very useful and not real complicated. It can become complicated, and we're going to look at a few of those, but in most cases it's not so hard. You just have to remember the formula. All right, x squared natural log x. So I have logarithmic and algebraic. Well, logarithmic is first, so that means that u is the natural log of x, and dv is x squared. So when I integrate x squared, I get x cubed over 3. When I take the derivative of natural log x, I get 1 over x dx. So my integral becomes uv, so x cubed natural log x over 3 minus v du. The integral of x cubed over 3 times 1 over x dx. Well, I can simplify that integral a little bit. It gives me x cubed natural log x over 3 minus, I can bring out the 3, 1/3, and that would just be x squared dx. So now when I integrate, the first part's done, x cubed natural log x over 3 minus, when I integrate x squared, that's x cubed over 3, but I already have an over 3, so this can now be over 9, and it'll be x cubed. And don't forget the cupcake. Okay? All right, here is when it can become a little more complicated, when you have two different transcendental functions. So e to the x is an exponential function, sine is a trig function, and they go back and forth, like the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of e to the x is e to the x, derivative of e to the x is e to the x. So it goes back and forth. So you actually kind of have to do a little bit of algebra here to make this work. So I'm going to let's see. So we have trigonometric and exponential. So trigonometric is first, so that means u is sine x, which means dv is e to the x. So v would be e to the x, du would be the derivative of sine is negative cosine. Nope, the derivative of sine is cosine. Okay, so I'm going to rewrite the original problem over here. We have e to the x sine x dx. And because they're transcendental functions where they go back and forth for derivatives and integrals, you're going to always want to rewrite out the problem in this case. So we have uv, so we have e to the x sine x minus the integral of v du. So we have e to the x cosine x dx. Well, it doesn't seem like I went very far. I'm going to have to use the integration by parts on that piece. So I'm going to change colors. So again, u is the trigonometric function. dv is the exponential function. So we know v is e to the x, and we know du, the derivative of cosine, is negative sine x dx. So we have e to the x sine x dx, the integral of that. That was our original problem. And that was e to the x sine x. Here is where I'm using this. So I have minus uv. So minus, and that would be all of this, uv. So e to the x cosine x minus the integral of v du. And because I have minus the integral and the du is negative, that becomes plus the integral of e to the x sine x dx. Now if you'll notice, these are the same. And if I distribute the negative, I'll have a negative, negative, and that would then be positive. So now I can add this e to the x sine x to the other side, so I have two integrals of e to the x sine x dx is equal to e to the x sine x minus e to the x cosine x. And all I have to do to solve is divide both sides by 2. And don't forget the cupcake. I should have had it up there, actually, as well. Okay? That is tricky, but when they're transcendental functions, that's how you're going to have to work it. Okay? So that's the first kind of more complicated kind of looking thing. All right. Arc sine. Remember, arc sine is really just inverse sine. And you may say, well, why am I doing this? Why am I integrating inverse sine? Well, first of all, it's a definite integral, so I want to show you how that works. And secondly, I just want to show you how inverse sine integrates. Yeah, just for the heck of it. Okay? So, you'll notice that Leate is logarithmic inverse. Inverse is second. So that means u is inverse sine x, and dv will be dx, which means v is x, and du, so the derivative of inverse sine is the derivative of x over the square root of 1 minus x squared. So this becomes uv, so x inverse sine x minus the integral from 0 to 1 of v du. And you'll notice that a u substitution can be used on that second integral there. So I'm going to use u substitution again. I'm going to say u is 1 minus x squared. Du then is negative 2x dx. And so I'm actually integrating u to the negative 1/2 du. But I have an extra negative 2 there, so I'll put a negative 1/2 out front. When I integrate u to the negative 1/2, I get u to the positive 1/2 times 2 plus c. So that really just becomes negative u to the 1/2 plus c. So, coming back over here to the original problem, the x inverse sine x stays there, and then minus, let's see, u to the 1/2. So u is 1 minus x squared, and it's not plus c, it's a definite integral. And because the definite integral was on the entire problem before, it stays on the entire problem now, which I know seems a little weird, but that's how it works. So now I have to plug 1 into everything. So I have 1 times inverse sine of 1. So when is sine 1? Well, that'd be pi over 2. Minus 1 minus 1 is 0. The square root of 0 is 0. Minus, now plug 0 in. The whole first term would be 0. Minus, and then I'd have the square root of 1, which is 1. So I end up with pi over 2 plus 1. I have to go back and fix one little thing here that I didn't catch. Notice this is minus, and I had it there, but when I integrate, that's a minus there, so this turns into a plus, which means then that this is plus. So this is really pi over 2 minus 1, which if you type that into your calculator, it's approximately 0.5707. Now remember, we can type this into our calculator and evaluate this as well. So if we type this into our calculator, and evaluate, we'll get the exact same decimal approximation. So, just an interesting problem, not necessarily for you to do it that way, but an interesting problem nonetheless. All right. I've asked you to use the formula for the integral of the natural log of x, but I've never proved it. So here we are, we're going to prove it. So Leate, logarithmic, that comes first, so that means that's my u. So my u is natural log of x. So that means dv is just dx. So that means if I integrate dx, I get x. When I take the derivative of u, I get 1 over x dx. So this becomes uv, so x ln x minus the integral of v du, so x times 1 over x dx. So I have x, natural log x, minus the integral of just dx, which is x, which is what your green sheet rule says. Just don't forget the cupcake. Okay? Last problem, and probably the most complicated of the problems, is x squared sine x. So we have algebraic and trigonometric. So that means algebraic is the u. So x squared is u. dv then is sine x. So v would be, whose derivative is sine, be negative cosine x. And du would be 2x dx. So we have uv, so negative x squared cosine x, minus the integral of v du, but minus a negative cosine makes it plus the integral of v du, but that means it's going to be 2x cosine x dx. Well, you'll notice I still have an algebraic function and a trigonometric function. So because the power decreased by 1, I'm only going to have to do this one more time, but I am going to have to do integration by parts again. So this time our u is again still algebraic, but 2x. Our dv will be cosine x. So that means our v, whose derivative is cosine, is sine. du is going to be 2 dx. So my problem starts off the same, negative x squared cosine x, plus, and then I have to go here. So I have uv, so 2x sine x, minus the integral of v du, so 2 sine x dx. So we have x squared cosine x plus 2x sine x. And if I integrate sine, I get negative cosine, but because of that negative, that's plus. So that'd be plus 2 cosine x. Don't forget your cupcake. That's about as complicated as integration by parts can be, but it is a very powerful tool for integration and one that you will need to know well all year long.